This is Advanced Placement Precalculus, lesson number 9. Today we're going to be looking at combining functions algebraically as well as composition of functions. Let's take a look at what we've learned about the 12 basic functions. So the first function we looked at was the identity function, where it's a straight line. It could be at an angle, or it could be horizontal or vertically. Then the cubic function, we have one particular curve, it kind of levels out and then has another curve that goes up. We're going to be entering and exiting in the same direction. The square root, which is unique because it does not have any negatives to it unless it is translated. The natural log, we have the cosine function along with that. I would throw in the sine function. They look very, very similar. The greatest integer function, where it looks like stair steps going up. And we have the square function, the parabola, what was often looked at when we were in Algebra 2. The reciprocal function, where we have 2. It looks very similar to the natural log function, but it is going down continuously throughout the entire graph. And we have the exponential function, where it is raised. Absolute value function, which is the V shape, and then logistic, where we have exponential growth, but it is limited to a maximum amount, and so we have asymptotes both below and above, so it's bounded in both regions. So that was what the 12 basic functions are looking at. Yesterday in our lesson, we looked at how we can better understand the equations of those, and we did a lot of work with the homework in order to help us have a deeper understanding. So that brings us to what we'll be learning today: combining functions algebraically. What are the 4 basic operations in mathematics? You learned them when you were in elementary school. We have addition, subtraction, multiplication, and division. We can do the same 4 operations with functions. We can add 2 functions together, we can subtract them, we can multiply them, or we can divide them. If we take a look at addition, we have f plus g of x is equal to f of x plus g of x. So when you see it written in this form, with the parentheses f plus g, and then in the parentheses, and then an x inside a second set of parentheses, you need to understand and be able to translate that to f of x plus g of x. The same is true with subtraction. If we have f minus g of x, that is f of x minus g of x. Multiplication, we might have fg of x, in which case that indicates that we are taking the function of f of x and multiplying by the function of g of x. F divided by g of x is the f of x function divided by the g of x function. In each of these scenarios, whatever our original domain is going to be true with our final domain. So in order for it to be in the domain of our final answer, it has to fit both domains of our original functions, with one notable exception, which I'll get to, and that is this last one, where we have f of x divided by g of x. Remember, I cannot have a 0 in the denominator. So I might have an extra limitation on that particular function, because if I get a 0 for my g of x in that case, it would be undefined. So we do have to be a little bit more careful when we do the division to make sure we get the entire domain that is supposed to be there. So let's try an example of one of these. Let's go with the multiplication one. Here I have f times g of x. So I'm going to take my f of x function, which is x squared, and I'm going to multiply it by my g of x function, which is the square root of x plus 1. So putting those together, I get x squared times the square root of x plus 1. So what is the domain of the new function? Well, let's go back and take a look at the domains of the original functions. What would be the domain of x squared? X squared has no limitations. It can be all real numbers. So that one we don't need to worry about. What about the square root of x plus 1? In order for that function to work out, we cannot have values of x that are less than -1. If I use a -1, I get the square root of 0, which is 0. If I had a -2, I had -2 plus 1, which is -1. I cannot take the square root of a negative number. So I am limited in my domain to the values of -1 all the way to positive infinity. Notice that the value of -1 is included. I have that open bracket there. Let's try subtraction 1. Let's do f minus g of x. Well, I'm going to take my f of x function, which is x squared, and I'm going to subtract the square root of x plus 1. It's really that simple in this particular case. Don't get too lackadaisical, though. In some cases, you might be able to combine like terms and things like that. So you do want to check to make sure it doesn't simplify down at all. In this particular case, it does not. What is our domain? Well, once again, I have all real numbers for my x squared function, and I have values of -1 to infinity for my g of x function. Here I'm going to be limited to that same domain of -1, including all the way out to infinity. Let's try the addition, f plus g of x. F plus g of x is going to give you x squared plus the square root of x plus 1. What's the domain? The domain is the same as we've had the other 2 times, and that's going to be from -1, including that, all the way out to positive infinity. And now for our final operation with our functions, and that is of division. Let's take f of x and divide by g of x. When we do this, we have x squared over the square root of x plus 1. If you rationalize that by multiplying by the square root of x plus 1 over the square root of x plus 1, you get x squared square root of x plus 1 over x plus 1. You do not need to worry about rationalizing, but I thought I'd throw that in there just to kind of refresh your minds from Algebra 2. So either one we can use. Now, what is the domain of our function? Our new function has a domain that is very similar to what we had before, but one notable exception. If you remember, when we're dividing, we cannot have a 0 in the denominator. So if I set this value right here, the square root of x plus 1, equal to 0, the only value that it would now exclude would be the actual value of -1 for my x. So my new domain is now -1, not including that value, all the way up to infinity. So you'll notice that up here I had the bracket, down here I have the parentheses, because this -1 value is no longer capable of being included in my function. If I were to do that, I'd get something that would be undefined. Let's try g of x, or you could think of it as g squared of x. What do you think I would need to do here? In this particular case, I'm going to take the square root of x plus 1, and I'm going to multiply by the square root of x plus 1, or take that whole square root and square it. What happens when you square a square root? The square root goes away, and you're left with simply x plus 1. Now, what is my domain for this new function? Well, if that was the only part that we knew, we would say it's all real numbers. I could plug in any value for x and come up with a legitimate answer for my g of x. However, we need to remember, where did we start? Where do we come from? Our original domain had the domain of -1, including all the way out to infinity. So that is also going to be the domain of my new function, -1 all the way out to infinity. So that brings us to the next part of our lesson, and that is the composition of functions. So what is a composition of functions? Well, let's step back and think about, well, what's a composition in English? When you go to grammar class and you make a composition, what you're doing is you're taking different parts and you're putting them together to make some sort of cohesive arrangement of a story or of information. You're composing, you're making something out of different parts. If you compose music, you take the individual notes, you put them together in such a way to where hopefully it sounds like great music. Well, the composition of functions is we're taking different functions and we're putting them together, not by the four basic operations of addition, subtraction, multiplication, and division like we just covered, but rather what you're doing is you're putting one piece into another piece. A composition indicates that we are applying function operation in a certain order. So let me give you an example of this. Let's just say that I have f of x that is equal to x squared minus 3, and I have a g of x function that is equal to 2x minus 1. What I'm going to do is I'm going to say, well, if my x value is a certain amount, I'm going to input, when we do the composition, a composition looks something like this. So something like G composed of F. What does that give me? Well, here's what we're going to say. Let's just say, as an example, that X is going to be equal to 3. So what I do is I take my 3 value for X, I'm going to plug it into my f function. So when I plug it into the f function, I get 3 squared minus 3, which of course is 9, minus 3, which is 6. So my output is 6. What I'm going to do with that output is I'm going to use it as my input value for my x in my g function. Well, my g function is 2x minus 1, so I have 2 times 6 minus 1. 2 times 6, of course, is 12, minus 1 gives me 11. So my final answer of the composition of g composed of f is 11. So I'm plugging in a value in one function, finding out what that output is, and I'm using that output of my first function as the input of my second function. Now, let's go about it a little bit differently. So rather than having to do this process for each individual value that I want, instead of just plugging in 3, and then I need to know what 5 is, and then I need to know what 8 is, and having to go through all this process multiple times, what we can do is we can combine or compose f or g of f of x. And then whatever values we need, we can just plug into one function and find out what our output value is and skip all this middle process. So f composed of g of x, we could rewrite as f g of x. We can see it in either one. So you need to recognize that these are equivalent in what they are saying, because the book could give you this value or it could give you this value. The same is true on the AP exam. So you want to make sure that you recognize them as being equivalent and know how to work each one. This means that you substitute the value of g of x in for the value of the f of x function, which is what I just demonstrated just a moment ago. I did it reverse, where I substituted in a value of g in for f, or f in for g. So let's just say that f composed of g of x, we want to find that when f of x is equal to 2x and g of x is equal to x plus 7. So rather than plugging in individual example points, what we're going to do is we are going to combine the two functions into one, a composition of functions. So what I do is I'm going to take my g of x function, which is x plus 7, and I'm going to replace that value, x plus 7, into where I have my value of x in my f function. So that would give me 2 times the x plus 7. And of course, 2 times the x plus 7, if I distribute, gives me 2x plus 14. So my composed function is 2x plus 14 if f of x is equal to 2x and g of x is equal to x plus 7. And then at that point, if I knew what my value of x was going to be, I could simply plug it into this equation and have my answer spit out immediately as opposed to going through all those intermediate steps. I do want to point out that in most cases, your f composed of g is not going to be the same as g composed of f. So unlike multiplication where a times b is the same as b times a, when we're doing compositions, that is not always going to be the case. And we'll see that as we work out some of the problems, even in your homework tonight. So let's try this one as another example. Let's say if f of x is equal to e to the x and g of x is equal to the square root of x, we want to find f composed of g. I'll give you a moment, see if you can work it out, and then think about what your domain might be. On this one, I'm going to start teaching about how we find the domains of compositions. So the answer here, I've got f of g of x. I'm going to substitute my g of x value, which is the square root of x, in for the x value in my f function. So rather than e to the x, I'm going to have e to the square root of x because that's what the g of x function is. So I have e to the square root of x. Now, what values can I plug in for my x? Am I limited in my values that I can plug in for x in this function here? And the answer to that is yes, I cannot plug in anything that is going to be negative. So my domain is going to be from 0 to infinity for that. That is also going to be true when I come over here and I have e to the square root of x. My domain is going to just be from 0 to infinity. Am I limited in my exponent values there? No, I could have a negative exponent value, I could have a positive, I could have a 0. So the second piece is not limiting. What is limiting is that square root, because I cannot take the square root of a negative. Now, let's switch the two, and you can see that they are not going to be equivalent. What is g composed of f? So this time I'm going to take my x value, which is e to the x, and I'm going to plug it in for my value of x in my g function. So I'm going to have the square root of e to the x power. So what is the domain of this particular function? Well, in my original here, if I have no negative values here, on my second function here, e to the x, that one there, I can have any value for x. I can have a positive, I can have a negative. That is not going to matter. So what is the domain of my new function? Well, based on my final equation, I cannot have a negative value in my square root. But is there any way to get a negative value in my square root based on this function? And the answer to that is no. E is a constant. It's one that we're going to learn later on. We probably touched on it last year in Algebra 2 honors. But it is a value. It's roughly 2.7. It keeps on going, but it's a non-terminating, non-repeating decimal, and it's a value that is positive. So no matter what exponent I use, even a negative exponent is going to give me a real value for my final answer. And so my domain is all real numbers. I am not limited to my values of x. If we were to graph these, this is what they would look like. So I've got my red line here. That is this function here, g composed of f. You'll notice that it goes into the negatives and it keeps on going. 0 is going to be an asymptote because it can never go down into the negatives. Whereas my blue function up here, f composed of g, starts at 0 and goes off to positive infinity. I also want to note that there are two values that these two functions are equal to each other. That would be the value of 0 right here, and then a value that is equal to 4. So if I were trying to test if these two functions are equivalent, having it graphed tells me that I cannot use those as test points because I will actually get false positives in those particular case that they are equivalent functions. So I would want to use different numbers whenever I'm trying to test to see if they are equivalent to each other. Try this one. F of x is x squared minus 1 and g of x is the square root of x. I want you to compose the f composed of g function. So f composed of g, that means I need to start out with my g values. If I plug in my value of g, which is the square root of x, in, or x variable here, that means I have the square root of x squared minus 1. Well, the square root of x squared is simply x. So I have x minus 1. So what is the domain of my function? Well, if I take this final here, I have no limits. I can plug in positives, negatives, zeros. I have no limits as to my function there. But what about the original input values that I have? In my original, I cannot plug in a negative value. If I look at this function right here, I cannot plug in a negative value. That would give me an imaginary number, which would not work. Therefore, my domain is going to go from 0, including it, all the way out to infinity. If I were to look at the graph here, you can see when graphed, I start at 0 and go off into positive infinity. Try this next one. G composed of f, that means I'm going to take my f function, which is the x squared minus 1, and substitute it in for the x value in my g. So I have the square root of x squared minus 1. What can I do as far as the domain for this one? Well, are there any limitations in my f? No, I can use any values I want to in my f. However, in my final, I cannot have x squared minus 1 being a negative value. So we're actually going to have a disjoint here. Let me give you a moment to think about it, and then we'll look at the final answer. In this case, it goes from negative infinity all the way to negative 1. So I can use very large negative numbers, even a negative 2. Negative 2 squared is 4. 4 minus 1 is 3. I could take the square root of 3. However, I cannot use something like 0, because 0 squared would be 0. 0 minus 1 is a negative 1. I'd be taking the square root of a negative number, and that will not work. At the same point, I can use very large numbers, values greater than 1. So it doesn't include anything between negative 1 and positive 1, but it includes all the other values. So I've got a union of sets here going from negative infinity to negative 1 and including, and then picking up at 1 and going on to positive infinity. If we look at the graph, this is what it would look like. You'll notice that there is nothing in between the negative 1 and the positive 1 values. Decomposing functions takes a little bit different thought as well. Some of them are going to be easy, some of them a little bit more challenging. We're going to show you a wide variety of these types of problems, but I'm going to give you a couple of hints just to help you along as to how to decompose. So reversing the process can be quite a challenge depending on what it is. So here's the first thing I would encourage you to do. When you look at the functions, try to find something that's similar. What is reoccurring in those? Well, I notice that I have an x plus 1 in parentheses in two different pieces. So I will look at, can I replace the x plus 1 as my x value? So if I were to say one of my functions was the x plus 1, what would the other function be? Well, if I look at f composed of g, let's just say g of x were the x plus 1. If the g of x were the x plus 1, then that means that this original function here, my h of x, instead of x plus 1 quantity squared, I could replace that with just an x because what is the x being replaced by? It's being replaced by whatever the g of x is. So this is going to be x squared minus 3x plus 4. X squared minus 3x plus 4. And I've now decomposed my function. Try this one. If h of x is equal to the square root of x cubed plus 1, what would f of x and g of x be if h of x were f composed of g? There are a couple ways of doing this one. I'm going to show you both. One is to say, well, everything inside my radical is my g of x. So I could say g of x is equal to x cubed plus 1. When I do that, that makes f of x simply the square root of x. That's one way of doing it. The second way of doing it would be to say, well, I'm going to have inside my radical an x plus 1, and then my g of x will simply be x cubed, because then when I replace the x with an x cubed, I get my original function that was the composition of the two. So in some cases, even on tests and quizzes, you might have a different answer than what I have. I would take a look at what your answer is and find out, is it legitimate? It could be that we just thought differently. You have a legitimate answer, in which case it will count. So as we go over these in homework as well, just realize that you may have a different answer than what I have. In many cases, I've added extra answers there because I've noticed that other people have different answers and they're legitimate. So just because yours is not listed doesn't necessarily mean yours is wrong. If you're in class, you, of course, can ask. So let's take some of this information and use it in word problems. This one, the volume of an angioplasty balloon inflated at a constant rate is V equals 8/3 pi r cubed, where r is the radius of the balloon. If the rate is 44 millimeters cubed per second, what is the volume after t seconds? So what it's saying is that we have a balloon that's being inflated by 44 cubic millimeters every second. So how long would it be after 1 second? It would be 44 cubic millimeters. After 2 seconds, it'd be 88 cubic millimeters. How am I figuring that out? I'm taking the 44 and I'm multiplying by whatever my value of t is. So my final answer would be V is equal to 44t, and that would be in cubic millimeters. Now, many of you probably overthought this, thinking that you're going to use all this equation right up here, but in reality, that's not what we needed at this particular moment. However, you will need it for perhaps this next part. Let's just ask, when the volume is V, what is the radius? So now I'm taking this function right here, V equals 8/3 pi r cubed, and I need to solve for the radius. This is using some basic algebra techniques, so I'll give you a moment. Go ahead and try to figure out what r is equal to. If you did it correctly, the first thing I would do is get rid of my fractions here by multiplying both sides by 3, or since I'm solving for r, I'm going to go ahead and multiply both sides by 3/8 to get rid of the entire fraction on my right side. And now I can divide by pi. When I do that, I get 3v over 8 pi, and then of course we need to take the cubed root of both sides to solve for r, giving me a value of the cubed root of 3v over 8 pi. I know that does simplify down because 8 is a perfect cube, but since we have fraction inside the radical already, I'm just going to leave it inside the radical to keep things most simplistic as possible. Let's continue on with the same idea. Here we have the question of write an equation that gives the radius as a function of time. So I do want to point out that we already solved that V is equal to 44t, and we already have the radius. But this time we want the radius as a function of time, meaning if I plug in a certain amount of time, I want to be able to find what is the radius of the balloon at that particular moment. First thing I would do is I would substitute in my equation here at the bottom that V for what V is equal to, which is 44t. Now I've got it in a relationship of time. I'm going to simplify the rest of my work here. So I take the 3 times the 44, I get 132. And then I can simplify the 132 over 8. That does reduce, giving me 33t over 2 pi. So I now have a function that relates the radius as a function of time. So one last question here. What would be the radius after 5 seconds? I'll give you about 10-15 seconds to work this one out. If you substituted in a 5 for my t there, you'd get 33 times 5, which of course is 165. You divide by 2 pi and then take the cubed root of it, and you should get an answer of roughly 2.972 millimeters is the radius of your balloon. So as a review of what we've covered today, we learned that we can do the 4 basic operations of addition, subtraction, multiplication, and division with functions. In order for it to be in the domain, it has to be part of the domain for both of my original functions. The one exception to that is when we divide, we might have some extra restrictions on that domain because we cannot divide by a 0. Then we looked at compositions. Compositions are inputting in our second function the output of our first function. So we replace the value of our first function in for the x of our second function in order to simplify those things out. The domain needs to be in the last portion of that composed function. When reversing the process, what I would encourage you to do is to look for the similarities between the two. And again, you might have multiple answers to the reversed or the decomposition of our functions.